All right, ladies and gentlemen, take a moment to get yourself comfortable because we will continue with the great sessions of today. We have another one lined up for now. I hope that you had some food, that you had some drinks. How are you feeling? Good. You okay, guys? You guys are there? All good? You had some food, I hope. You had some coffee at least, because we have also with us an expert with a decade of experience in software engineering that's going to help us answer one important question today. Basically, how do we choose the right data warehouse? What exactly is a data warehouse and which one is the right one for you? All right, so we have with us Andrew Miller, the founder of Qcelerate, and let's give him a warm welcome. Thank you.
Thank you. All right, brief introduction. Um, I run an AI/ML consultancy called Qcelerate. So I'm the principal consultant, but I've done data engineering and been an AI/ML engineer with AI/ML 9 years and overall 13 years of experience. I mainly support fintech, health tech, and legal fields, and I'm based out of Holly Springs, North Carolina. And I'm so excited for all of you to come to this talk today. So I wanted to ask folks, how many of you know what a data warehouse is? Raise your hand. All right, about 50%, great. So for those of you who don't, I'm gonna go over that, but I'm also gonna go over why you would want to have a data warehouse, and hopefully you come out from here wanting to build one or use one if your organization has a data warehouse. I'll also talk about how you would build a data warehouse and what would happen if you actually decided to build one. And then there will be some time for questions and answers. So what is a data warehouse? There's a couple of definitions that I think are relevant. One is from dictionary.com, and it talks about data warehouse being a large repository of data from various business units within your organization. Kind of a mechanistic approach to looking at a data warehouse. And then you have Wikipedia, which talks about reporting and analysis system. So it's more about the outcomes that you're going to get from this system. It doesn't really say, that it's centralized or distributed or whatever else. All right, so why you would need a data warehouse? So there's a lot of reasons why you would look to build a data warehouse. You might be having data integration issues. Your queries might be slow. Data quality in your organization is not great, or you have security and compliance requirements for your business. You might also have a lot of historic data, and with that typically comes scalability issues. And last but not least, you might be building AI/ML applications. So let's dive deeper into specifics. The first sort of class of problems are data integration problems. And some of you might have seen environments where you're trying to build an application or a report, but you have tens, hundreds of different systems that hold the data. And so then it becomes very problematic to query all of them, but also frequently you'll have like things like schema mismatches, format mismatches, and terminology mismatches. So now you're having to convert from one terminology to another and from one schema to another just to connect the data points. It gets really difficult and sometimes even impossible to get all of that done without that data warehouse. But let's say you figured that problem out and now you're running your queries. Traditionally, if you're using some like a transactional database, your query might be running for hours. And meantime, your database resources get exhausted, and your users might actually not be able to use the system. And by the time your query is done, could be 2-3 days, your data that you're getting back is, well, stale. It might not be up to date. And if you're an engineer, that's wasted time but for a business also, that's wasted time, so wasted money, labor costs. So the other kind of type of problem that you will run into are data quality problems. So let's say you worked out the performance issue. Now your queries are running fast. You can deal with converting between schemas and terminologies. But now, well, you're not getting quality results from your reports. For example, you're seeing duplicated data, invalid data, some data is missing or inconsistent, and even worse, ambiguous. You might be getting two different values for the same thing. Now go figure which one is actually a good one. If you're in regulated industry, what you might also be running into is security and compliance requirements. For example, if you need to share your data with a third party, another organization, you might need to anonymize part of the data, or you need to have certain access controls like RBAC. But in terms of security, you also want to make sure that it's easy to protect the data. So in the drawing here, you see a castle, and there is an entrance, single point of entry. Very common technique for building security into a system. And a data warehouse can give you that, because you don't need to guard 20 different systems where data is. You're just guarding the data warehouse one place, which could be a lot simpler than protecting everything you have. So you might also have historical data, and that typically amounts to a lot. And when you need to actually query it, it becomes very problematic for the reasons that I mentioned, like slow queries, or if, for example, data is archived in another system. Now you have to bring it from that system and connect it with the current data. So you run into all kinds of problems. And on top of that, in many organizations, your data is versioned. So now you need to make sure you're using the right versions. Or you could be running into situations where part of your data is versioned, part of it is not. Now you scratch your head, like, how do we connect the dots? So another type of problem that you can run into is scalability. Let's say you have all this historic data loaded in a database, a centralized database. Now you're trying to query it, but a database isn't just fast enough to give you the query in reasonable time. And the way that I like to look at this problem is UPS truck versus a train. You could lift some stuff with the UPS truck, but if you have too much, a train is probably going to be better. And also think about economies of it. A train might be a lot cheaper to do the same task. And so the train represents, a data warehouse. Another problem is a lot of sort of transactional database, operational databases that you use, they can only scale vertically. And so what that means is you're going to run into limits at some point. All right. The last and my favorite is AI/ML applications. Let's say you're building a chatbot. Your chatbot typically is going to be as good as your knowledge base. So if you have 20 different source systems and they're ambiguous, one says one thing, another says another, there's gaps in data. Now your chatbot might be giving really bad answers on top of the usual hallucination and just indeterministic behaviors. The other part of the problem is if you're creating 20 different systems just to send the results into a prompt, you might be waiting for a while, even if you query in parallel. So your chatbot becomes super slow, and chatbots typically, you expect sub-second responses. So this is another issue that you're going to run into. LLMs in general, limited context window. So you're gonna be very limited in terms of what you can send in with your prompt. So now you also have to filter the data. If you're talking about historic data, how are you going to do that? And you might be running, RAG, you might be running semantic searches, but in many applications, you actually have to query exactly like, here's the date range, here's the category or geographical location. And in those cases, like that semantic search isn't going to cut it. So you still need a data warehouse. And finally, I think the biggest appeal for a data warehouse, at least for me, is if your organization has data scientists, they will typically be asking you, is there just like one place where I can get all of the data and it's, top quality, the single source of truth? And for data scientists, it's the best thing they can get their hands on is a data warehouse. All right, so hopefully by now you're well motivated in terms of what you want to do or why you would want to build a data warehouse. So how would you go about building it? Well, in a nutshell, this is the process, and I hope it's barely readable for some of you. But on the left, you have your data source systems, so like operational databases, flat files, sensor data, ERP systems, you name it. You could be other sources. And typically you'll have some sort of ETL process. Now with the no ETL or zero ETL solutions, you still have to configure it. So there's still that step of getting data out of where it is and storing it in a staging area. And staging area is just basically somewhere where you can have access, a centralized access to the data. But it might not be standardized yet. It might not be converted to the same single schema that you're going to use, or might not be using the same format. And finally, once you have your data in a staging area, you then load it into a data warehouse. And once it's there, well, great. You can then consume it with your business intelligence or reporting apps, or from your AI/ML applications, either training pipelines or inference. So there's going to be a few important things to know when you build a data warehouse. And one of them is the access patterns. So if you're building a system that is doing a lot of like queries that are just, here's one data point that I need, as shown on the example on the left, where I'm just querying the specific GitHub issue with ID 23, that's called online transaction processing. And in terms of if you are writing, it would be, for example, a single insert statement where you might be doing, an insert of 10 or 100 records, versus, let's say you're doing something like an aggregate count of all of the GitHub issues that are open by author. So you're grouping by author and you're counting how many each of the authors has open issues. And that would be an example of online analytical processing. And if for reading. Now, if you're writing, you typically be doing bulk writes. I have a huge CSV file with, thousands of records. I'm just going to write it all out in a table. So that's an example of OLAP access pattern for writes. Now, a lot of applications, what happens is, well, you're going to have transactions, but you also have analytical stuff. So now you kind of need both. So what your data warehouse is going to be two separate database systems, or how is that going to work? So HTAP is kind of both an access pattern, but also a class of database systems that support this access pattern, where in essence you're hybridizing the database so it can handle both transactional and analytical workloads. And it's a growing market, and my kind of theory on this is that in next decade there won't be OLTP or OLAP. Everything is just going to be hybrid, and we're already seeing it. Like examples are single store and TiDB. Now, when I say OLAP or OLTP, what's important to know is what's under the hood and how is the data stored. And typically an OLTP or transactional processing system will store data row by row, and there will be blocks of those rows. So then if you are, for example, trying to read a record, like an example with GitHub issue with ID number 23, you're gonna locate where that record is on disk or storage device, read that whole block, and then read that specific record of the block and surface it to the user. And this works okay. Now, it doesn't always work, and we'll get to that. But it's heavily optimized for writes, because you could just write one record after another and dump the whole block. There's another way of storing it, which is column oriented, where you're going to store each column as a separate sequence of blocks, and you're just storing value after value in each block. And that pattern is optimized for analytical processing, and we'll see how and why that is in a moment. So yet another thing to know is, let's say you're building a data warehouse, how you're going to model the data, what's the schema for the data. So typically, if you're having an operational database, it will be in some sort of normal form, or you're going to be striving for a normal form. So your schema is very optimized for inserts, but it might not be optimized for analytical queries where you're trying to aggregate across multiple tables. And the tables typically will be wider. So then if you're working with a row-oriented database, now you're lifting very wide rows, and a lot of them, that's a lot of read time. Now, if you're building a data warehouse with a traditional, OLTP database, you can do some optimizations such as star or snowflake schema, where in essence what you're going to do is you're going to create two kinds of tables, a fact table and then dimension tables. Like in the example of sales, you might have, and sales are basically events. So then you'll have a fact sales table where you're capturing IDs of different dimensions of that fact. So the types of dimensions you might have are customer, date, and then if I read it right, product, what product you're selling. And this is a toy example. Obviously, you're going to have potentially a gazillion of different dimensions. Typically, the dimension tables will be very narrow, and they'll be not as long, so your joins are going to be more efficient than if you were working with a normal form. So that's one way to kind of optimize. And before columnar databases existed, this was very common to leverage, because it allowed you to read less data. Because, for example, if you're querying, if you only care about customers, you don't need to touch the product and date dimension at all. Now, your joins, you're only doing one join potentially, and it's becoming more efficient because you're not reading as much data from disk or storage device. And finally, the other technique that a lot of organizations use is called one big table. And this idea is you just jam everything to a single table. You might have duplicate records. That's okay because you don't have any joins, and joins are expensive. So then you're just doing, a filter. If you have indexing and things like that, it could be very, very, very efficient. But this approach, data scientists love it because it's easy to dump out and load into something like pandas. And I frequently see data scientists try to, if they're working with an operational database, query the database and then jam everything into a single table before they can pre-process and train on that data. So if you already have your data in one big table, could save you some cycles for data scientists. All right, so I mentioned like I'm going to show the difference in terms of read times. So this is an example of an estimate. let's go back to kind of the queries that I was talking about, which is GitHub issues. Let's say I have 100 projects every year, and each project has 3,000 issue events in it. And let's say I'm retaining data for 5 years. We're going to estimate that each issue is roughly 700 bytes. So 7 fields, each field is 100 bytes. If you're using AWS GP3, SSD baseline access rate of 125 megabytes, you can get more, but like this is just very basic, stock sort of a storage device you can get. And let's say there's no indexing. In reality, there will be indexing, but we're just comparing, raw power of row-oriented versus column-oriented databases. So if you run the math, your data set will be about a gigabyte. And with the access rate that I showed, it'll take about 8 seconds to lift that from the storage device. You'll have, of course, like the scan. If you're doing just a sequential scan, that's what you have. It'll be negligible compared to the 8 seconds. Now, let's look at column-oriented. Let's say I'm just doing 2 things, grouping by and a where clause. Now, with column-oriented databases, I don't need to lift the entire row to fulfill this query. And let's assume data is not compressed, and let's assume that there's no distribution, partitioning, or sorting done. So again, comparing raw power, row-oriented, column-oriented. If you run the math, you're only lifting 2 columns, like I showed in the query before, which is group by author and get the status open. For lifting 2 columns, you're only lifting 2/7 of the entire table. So you end up reading 300 megabytes, which, if you do the math, is about 2.3 seconds. So you can see it's almost 4 times faster just to do it, pure raw comparison versus a row-oriented database. That's why these databases exist. All right. So let's say you're convinced now, I want to build a data warehouse. I think I'm going to have HTAP. I'm going to have both row-oriented, column-oriented in there. It's going to be great. It's going to work for everything. So how would you go about actually building the schemas that I showed you, right? Let's say you pick star schema or one big table. Well, a common pattern is called create table as select. And what this allows you to do is take an existing table or multiple tables and select from them. And in the process of selecting, you could apply some transformation. So in this example, what I'm doing is I'm converting first name to uppercase. This is just an example. Obviously, you might be doing something more clever, like maybe I want to capitalize, the first letter of the first name. Probably not the best example, but you could also be doing something like, convert from Fahrenheit to Celsius, because you don't want, records that have both, because that's more difficult to query. Then you can also transform your terminology. Like, for example, here I have type code with the values std and prm, but in my data warehouse, I like to have everything nice and neat. So I will actually convert that to standard and premium. And it could be that one source system has std, another source system might say s. So this approach allows me to just run create table as select and I can even say, like, for this source table, do this. For the other source table, do something else. But at the end, all of my values will be standardized. So that's just an example, and this is a very useful tool, very frequently used in data warehousing when you build a data warehouse. All right, another important thing to know is symmetric multiprocessing versus massively parallel processing. What does that mean? So symmetric multiprocessing, that's kind of what we had for many decades. You have one server, and in order to scale the computation, you have to basically add more CPUs, add more memory, add more storage. But it can, take you so far. Like at some point, you're going to run into limitations of that single server. So then MPP will allow you to add more servers. And theoretically, let's say your query takes 3 minutes with MPP. If you have 3 nodes, if you can distribute everything perfectly, at most you can get the query now running in 1 minute, which is still good, right? 3 times the speed up, theoretically. In reality, of course, you're not going to get that. And you still have vertical scaling because you can scale each node, but you also now have horizontal scaling. You can add more nodes. In this example, I show like storage as a separate box in each node. Modern vendors, storage scales independently now with most like enterprise vendors. So that's not really a concern anymore. All right, so let's say you're convinced you now have the tools necessary to build a data warehouse. So before you actually do this, you'll probably ask yourself, well, but what happens if I do, like, you saw the benefits, right? But what else? Are there any gotchas? So there's actually many decisions you're going to need to make before you build one. Aside from the ones that I showed you, like, is it going to be SMP or MPP? Star schema, one big table. How, like, am I going to use create table as select, or maybe I'm going to use some other technique like ETL, or maybe I'm going to combine it. So a lot of decisions, but you'll also have a lot of vendors like BigQuery, Databricks, Postgres. Maybe you want to go with Snowflake or Redshift. And, am I going to build Lakehouse architecture or Medallion architecture? There's going to be a ton of choices you're going to need to make. And these choices are going to come with pros and cons. So this is probably, I don't know if that's readable, but I'm going to just talk through it. So in this example, comparison between Postgres, Redshift, and Snowflake, I'm picking certain things that personally I would look out in a data warehouse system. So we talked about, row-oriented versus columnar. So you can see here Postgres is row-oriented, and you have Redshift and Snowflake, which are columnar. What I care about is also MPP versus NMP. So stock, vanilla Postgres is going to be SMP, scale it vertically, versus Redshift and Snowflake. I just scale by adding more nodes, so they're MPP. The thing that I also care about a lot is developer productivity, engineer productivity. And so what does it take for me to scale a database? Well, with Postgres, somebody is going to need to go and manually do it, unless you're using something like Aurora. But even there, you still have the setup versus Redshift, Snowflake. That's all automated. Very similar with things like, we're talking about Postgres. You want to optimize your queries. Now you need to set up indexes, optimize queries. Most of the time, all that is manual. There are tools that automate this, but you're going to pay money for it. So it's labor one way or another. You're just paying with, one way or another for that labor. Versus Snowflake, all of those optimizations for the most part are automated for you. So it saves a lot of engineer labor time for you. And Redshift, I think they're working on automating more and more of this. So it's getting better. All right. Another important thing for me personally is the ecosystem. If I'm coming in to an implementation and, right now I know the requirements, but tomorrow another, dozen requirements might come in. And now how do I fulfill them? Well, Postgres, it has a very rich ecosystem of extensions. So I know that for a lot of things, if the client is asking me for that extra thing, I can just leverage an extension. Versus Redshift, so you have user-defined functions and good integrations with AWS. But if you know that you're going to need to go beyond AWS, might not actually work too well. And for Snowflake, well, it's going to work in any cloud. So I don't need to worry about network connectivity. I can deploy it in any cloud I want. I can get the permissions working in those clouds. And also there's good multi-region experience, which I care about. So that's me. You might have a completely different set of dimensions that you're, judging your solution by. The other important factor for me is shading. So let's say I have my data warehouse in Postgres. How am I going to share data with a third party? Well, I need to use foreign data wrappers, and things get really complicated, a lot of manual effort, versus something like Redshift or Snowflake. Well, it's very simple, and you can share across different regions, across different clouds. They really like simplify this process. So if I know I'm going to need to share data, I'm probably not going to go with Postgres because it's so complicated to share data with Postgres. And finally, regulated industry, you're looking at anonymization. A lot of times when you are sharing data, you don't want to, share all of it. You might be masking like things like social security numbers or whatever other, identifiers you have or sensitive information. And Postgres comes with an extension called Postgres Anonymizer, but it's not available in AWS. So if I know the client is in AWS, I'm probably not going to recommend Postgres. Redshift and Snowflake both come with their own data masking solutions, so I don't need to worry too much about those. All right. So I talked kind of about the comparison, but there's a financial aspect to it, because these decisions, like each of the dimensions, is also going to translate to costs. So what kind of costs am I going to have? I'm going to have labor costs for paying data engineers for building ETL pipelines or configuring no ETL solutions. I'm going to pay those same data engineers for query development, for data quality checks and test development. And then I'm going to pay site reliability engineers or DevOps engineers for standing up the infrastructure, for configuring access controls, and also setting up monitoring and alerting. And so that's my labor cost, but there's another aspect, which is infrastructure costs. So I'm going to either buy hardware or I'm going to rent it. And then if I'm renting, I'm going to have data transfer fees, shading fees, depending on which cloud infrastructure provider you're using. And if you're self-hosting, then electric bills is one of the considerations. Or if you're using something like Snowpipe or Redshift, you have additional costs like S3, SQS, or Snowpipe, and also authentication. That also costs money. All right, so then for labor, that's going to be like dependent on where you are, right? Poland, one rate, Lithuania might be another rate, US, yet another rate. And your choice is going to be, predetermined by a lot of factors like, what vendors you have available to you, your budget, and the time, you have to recruit these people if you don't have them available in your organization. So I'm not going to cover estimating that because that's a whole separate talk. But I am going to give an example of estimating infrastructure costs. So in this example, now the numbers might be out of date, and I'm sorry for dollars. I didn't bother converting it to euros because this is an example. This isn't exact comparison, and you'll see why. It's kind of napkin math that you want to do upfront. So first, kind of a problem is that if you're using Postgres, Redshift, or Snowflake, there's no one-for-one comparison. There's no one node configuration that you're going to get across all of them. So you're never really comparing apples to apples. It's always like apples to oranges. In this example, I'm assuming US East 1 because that's what I use frequently. And also, if you're using Snowflake, good luck because they don't give you a cost calculator or pricing calculator. So you're on your own trying to figure out how much it's going to cost. You probably want to actually run your workload and estimate based on running your workload. So Snowflake will use a thing called credits, and then the credits will be used based on, well, how long you use your warehouse, but also if you're using cloud features like Snowpipe, that will also take those credits. Let's assume we're not using Snowpipe, and let's assume our warehouse is running 24/7, so 730 hours per month, and we're using the standard plan in Snowflake, which is $2 per credit and 1 credit per hour. And then we're paying $23 per terabyte. So if you run the math, you see that Postgres comes out to be the cheapest, but it's a row-oriented database, so you're probably going to run into slowness and things like that. I'm going to have to optimize, indexing and queries. So you're going to pay, even though it's the cheapest, you're going to pay in labor costs doing all those optimizations to get it to work. Redshift, a little bit more than Postgres. And finally, Snowflake comes out to be a lot more. Now, the reality of it is, if you're like, a global shop and you have, your team distributed across, and your user base distributed across the globe, you're probably going to run 24/7. But if you're, localized in like, Eastern Europe, for example, well, you're probably not going to run it 24/7. You're probably going to be running it 8 hours if that's where, most of your active use is going to be. So then that cost actually drops drastically. You can easily recalculate. So it's really going to depend on, what your usage pattern is and where you were based out of. So that's it in terms of going over, how you would build a data warehouse, how you estimate the costs and investments, and the different techniques you might use. So thank you for coming to this talk. You can connect with me on LinkedIn or just email me. And now is the time for questions and answers.
From the audience, or should we go with these questions on the screen? Andrew, would you like to take questions directly from the audience or from the screen? What do you prefer?
Either way works. Maybe let's start with the Slido questions.
Yep. Okay. So, do you find data lake useful, or is it just an unnecessary hype?
Yes, it is definitely useful. I would say that it depends though on your environment, on what you have available. It could be just a waste of your time too. So the answer is it depends.
Some example. Okay, we have this next question. Some examples where a data warehouse could be better off data lake, lake house nowadays. I'm not sure if the question is properly formatted.
All right, I'm rereading it.
Yeah.
Some examples where data warehouse could be better off than data lake house nowadays.
Feel free to write the question again if you want to retry it.
Yeah, I'm gonna say is if a lot of your data is coming from like S3 and systems like that where it's not very structured, you might not have a lot of operational data stores. I think Lakehouse could be actually a better solution in that setup. But if it's like mostly operational data, transactional data, I think a data warehouse is still going to work better.
Gotcha. Next one. You're sharing PK, FK relationships in DWH. Most of OLAP tools can't ensure it. How would you suggest to ensure referential integrity in DWH efficiently?
Yeah, the answer is don't, because that's not what data warehouse is for. You typically enforce that in your operational data store, and then once the data gets into your data warehouse, those constraints should already be satisfied. Now, if you're working with a system where that hasn't happened, now you're going to have to figure out how to prettify the data or improve the quality of it. And the answer is going to be depends on what kind of data you're working with. Basically, it's going to be domain specific to the data type that you're working with to make it satisfy those constraints. But like the stuff that I was showing with create table as select, you might be actually incorporating certain things in that to enforce that you don't have things like duplicates or basically the constraints of your data are satisfied.
Gotcha. Would you suggest Snowflake Infra, pros and cons?
I'm not a Snowflake expert, let's put it this way, so I wouldn't suggest anything. And again, the answer really depends. There is no like right or wrong answer. we have to look, and I'm a consultant, right? That's what I do. I come in and look at your problem, figure out, what is actually, what you have available, what's your budget, and then make a suggestion. But just kind of a, rule of thumb, there's, in my book, there's nothing like that.
Gotcha. And maybe one last question we have here. What is your view on the future of data warehouses considering the AI wave? Companies like Microsoft and Databricks are heavily investing in AI and lakehouses.
Yeah, so like I talked about this in the slides, you still need a data warehouse if you're doing AI/ML. And in fact, the need for data warehouse is even more pressing than before because you want to have quality data. Sure, like we have AI that can, clean up data and you send in garbage, you get nicer data. But for most use cases, you want to send in quality data so you can get quality data back. So it's never been more important to have a data warehouse than now. Now, in terms of the other aspect of this question is like, how is data warehousing technology evolving because of AI? And that's where what I'm seeing is data warehouses basically are becoming more intelligent because now they can answer like questions in natural language. I went to an earlier talk from Databricks, and they were showing that like you could just interact with natural language. And I think what we're going to see, like things like maintenance, you have indexing set up, you have partitioning, all that stuff. You can throw AI at it. That's the promise, right? So then your data warehouse is automating all of that. You don't need to worry about it. AI will just figure out how to do that the most efficient way. Like all the star schema, on big table, let AI take care of it. It will analyze the access patterns. These are rules that actually you can use rules of thumb, like I was showing. If you have a lot of, transactions that you're writing, go with the normal forms, right? But if you have a lot of analytical queries, now this data needs to shift into a columnar store to be more efficient. But AI can do this. You just give it a sort of your SOP, and it will dynamically do this if you have a cycle that's running. So that's what I see with data warehouse vendors. It's just going to be a whole new evolution, and data warehouse is going to become a lot smarter.
Nice. Thank you so much, Andrew, for your expertise. Thank you, ladies and gentlemen, for the interesting questions. And stick around for the next session, maybe. Have a good rest of the day.
Thank you. Wonderful.